high-performance computing again. What I'm going to do in the next 20 minutes and then leave about 10 minutes for Q&A will be walk you through some of the deeper details and some of the background on our Radeon Instinct MI60 and MI50 accelerators. As David mentioned, this is the world's first 7nm GPU. Performance improves dramatically with it, but the key takeaway from it, and I hope you caught it earlier, but it's really about building a balanced GPU that is optimized for multiple different workloads, data types, data sizes, and applications. Really, this sort of journey to making a better accelerator started about 18 months ago when we started talking about our Radeon Instinct MI25 accelerators back last June. So give or take about 18 months. When we started it, we wanted to start very focused and really focus around FP32 type workloads that focus around visualization, leveraging our graphics background, but also getting into the machine intelligence space, focusing on FP16 operations as well. So a lot of things have developed over the past 18 months. Our software stack has developed dramatically, and the customer uptake and feedback has been fantastic. So what we have now done is we're starting to build an accelerator with MI50 and MI60 that covers the wider spread between speed, we're going down to inference with int8, and then even int4 operations, but also accuracy moving up back into the FP60 source space for high performance computing where accuracy really matters. So as I mentioned, we really started this with our machine learning training accelerator with MI25. We do address all these spaces in various forms. We do address virtualization with other products that we've announced recently. But we introduced our Instinct MI50 and MI60 accelerators, really focusing around machine learning training and HPC. Key differences between the two of them is, and I have a slide in 2 slides that talk about the real performance difference between the two, because David mostly talked about MI60, is that if you need ultra high performance, double precision, sort of if you're building that sort of exascale, highest performance system, and you need to have really large data sets fit into on-chip memory, MI60 is a fantastic accelerator for that. However, if you're developing applications and workloads that don't require the 16 gigabytes of 32 gigabyte HBM, and you can fit in within 16 gigabytes, but you still need that memory bandwidth, MI50 is a fantastic accelerator too. And I'll show you in a couple of slides that between the two of them, other than the HBM size, performance between the two of them is actually only about 10% delta if you look at the peak theoretical. So very fast in both avenues. But if you're working with those exceptionally large data sets that you need 32 gigs, we give you a little bit more performance there as well. But the nice thing is because it's a flexible architecture, there's high reuse. So there's 2 different scenarios where users might want to use, say for example, an MI50 accelerator for large batch inference right off the bat, or they might want to have high reuse, so during the day they do VDI services, at night for on-prem cloud, but at night they'll be doing their deep learning operations and algorithm training. It allows you to have a very flexible architecture where you're not really pigeonholed into one specific type of workload and one type of data set. Other application of that as well is that for large data center customers where they always want to have the fastest accelerator, so as new GPUs come out and they replace them with faster accelerators, there's high reuse, and you extend the TCO horizon of these because they can then be deployed out for other services as well where the peak performance doesn't matter as much, but you still get fantastic performance in other types of workloads as well. And then, call it, phase 1, phase 2, phase 3. In 2020, as David mentioned, we will have a new accelerator coming out that will be substantially faster, higher performance, a new architecture as well. So we do have a long-range roadmap in this area as well. So directly comparing the MI60 and MI50 accelerators, top-level difference, MI60 and MI50, it's about a 4 compute unit delta between the two of them. And what that really comes down to in terms of peak performance, where you're not interacting with the HBM, really you're talking about a difference about 10% peak performance. So up to 118 peak inference operations int 4, up to 107 TOPS for int 4 as well. But if you want to look at your traditional FP32 or FP16 numbers, you're talking 14.7 and 13.4. So still very fast, about 10% performance out there. Difference is, do you need 32 gigs or 16 gigs? But across the board, you get 1 terabyte of memory terabyte per second of memory bandwidth. You get the full memory interface. It both supports ECC. They're Gen 4 capable, and you get 2 links of Infinity Fabric on both these GPUs as well. The Infinity Fabric link is a really big thing to note here, is that we're offering it in a server data center form factor, in a standard PCI Chem form factor as well, which isn't offered by other competitors as well. So you get that high bandwidth interconnect in traditional server form factors as well. So in terms of the architecture, just by the speeds and feeds, David mentioned this, 13.2 billion transistors, 331.46 millimeters square, twice the density, greater than just over 25% performance, a clock uplift at the same power, or at the same clock about a 50% power reduction. I'll walk through the different components on here, but you can see that you have your 2 Infinity Fabric links, your 4 channels of HBM controlled, so 496-bit memory interface, and you have your 4 compute engines in each die.
Just to confirm, it's 13.2 billion, isn't it? Not 3.2.
Yes.
Are you missing
13, yeah.
I'm missing a 1.
You're the first person that caught on to that all day. Thank you, Trinder.
And you just won a Radeon AC.
Thank you.
You can pick one.
I will buy you a beer tonight.
I'll buy you one back.
Thank you.
So where does the twice the density dial into? Because the other chip is 480 something square millimeter, right? That's not a factor of 2.
So it's certain areas of the chip have higher transistor density. I can't remember which component of the chip. I'd have to actually go to my PR colleagues and get the claim for that. So I apologize. That's the one thing that is just not in the data bank right now. But really what I talk about is just sort of some of the optimization. This is what I really want to get to. That was more just sort of setting the stage here. So as David mentioned, we have dedicated deep learning operations on our Radeon Instinct MI50 and MI60 GPUs. We're calling this sort of making a better next-gen compute unit based off of Vega. So we have flexible compute units that allow us to do mixed precision deep learning for inference and training. But also, if you look at the vector ALU, we're going back to half-rate FP64, 64-bit operations as well. So that allows us to come back into the HPC space with high-performance accelerators. And the reason why I'm calling this out, because if you look at it, it's a block diagram between a Vega 10 compute unit and a Vega 20 compute unit. The layout looks the same, but it's just what we've done differently with them. When you look across the registers and the cache, they're now all ECC protected. So MI25 was only HBM ECC. Now we have SRAM ECC, so it's a full chip ECC solution, which is critical for data centers where you're looking at HPC, where any errors in the data could cause a miscalculation, and they want to capture and collect that. But digging down even further, and I don't really have a box to circle here, is that we did tweak the silicon, we did tweak the caches so that way they can run faster. This is outside the 7 nanometer process node, but also we tweaked the latency between the caches as well, so that will give us higher performance as well. So these are the numbers that David talked about earlier. So from the FP16 performance, it's 29.5 teraflops of FP16, about 20% faster than what we had on MI25. 59 TOPS of int 8, so it's 140%. So really, as I mentioned here, is that this is where we spent a lot of the effort making sure we can go down to int 8 and int 4 operations, get substantial performance improvement over the MI25 product. But we added new instruction sets here and mixed precision accumulators. So we actually can accumulate FP32, FP16 and INT16 and the smaller data types into the 32-bit accumulators here. So it just makes us more efficient, so you can load the GPU up and leverage efficiency, get more computational power per flop. And allows us to, and so we've done that, but also we've added a substantial number dot instruction sets across the board, and it allows us to do a lot of unique things across the board where we have a very unique and sort of flexible architecture for multiple data types rather than dedicating a lot of specific silicon to one data type. So you combine this with a terabyte per second of memory bandwidth, which is twice that of MI25, really focusing on huge data sets. And it comes down to a couple things. If you look at just straight matrix multiplication, sure, we're getting about 25% or higher if you look at an SGEM type number.
That's clock.
HGEM number.
That's clock based.
That's clock based. Clock based and engine based. But this is actually running. So this is basically just with the matrix multiplication capabilities of the chip. But when you look at the FP32 and FP16 accumulators, the new instruction sets, double the memory bandwidth. When you start looking at real applications using FP16 for training, this is where you actually start seeing the greater than 25% improvement, where you're up to almost 3x of improvement in application level. So that's why looking at raw flops doesn't necessarily tell the story anymore. And that's the real takeaway from here, is that you can look at matrix math, great. You really need to look at the application stuff. So big flops numbers don't necessarily translate to the same performance level they used to.
Does this require any optimization software size from the vendors?
So we will optimize at the framework level, so and our driver level to make sure we're efficient. But when you're looking at two things, we will upstream to say like TensorFlow to make sure that our operations, our code is optimized. And then you just work with your TensorFlow framework and you'll realize those benefits. But you set me up really easy here. Is that I'm not sure how many of you heard of CHIME. It's a Canadian hydrogen intensity mapping experiment. Basically, they're trying to map the solar system. And it's done between a couple universities, University of Toronto, University of British Columbia, and McGill University in Quebec. And what they have is Keith Vanderlyn, he's an experimental cosmologist, and he's been working with us on a number of different projects. So they have 2,048 antennas. They're currently using over 1,000 GPUs. They're using S9300 by 2. They're doing about 6.4 terabytes per second of data, and they're doing 12.8 billion ops per GPU. So we gave him access for an afternoon to our GPU using our S.8 operation, and he's like, I'm seeing huge improvements. What did he see over the S9300 by 2? He saw he was seeing about 500% performance improvement. I don't really want to focus on this. This is just a big number. It just shows how much you can speed up over a previous high-end server GPU. The key thing is that this is done in simple OpenCL. So it's in our driver. As long as you have our ROCm stack that's OpenCL enabled that supports the GPU, you can do the simple coding versus having to write thousands of lines of ASA code. So kind of like what you said. As long as you can call the operations in OpenCL, or if you're calling specific operations in your TensorFlow framework, you get access to this performance.
So it's quite easy to extract.
Yes. So he did this in an afternoon. We gave him remote access in the afternoon, SSH'd in. He was seeing improvements. He was going from 70 milliseconds for his operations down to 14 milliseconds in an afternoon. So he actually said it allows him to write code lazy. I won't go any further on that. We've all been programmers. Most of us have been programmers at one point or another. So if you can get by writing lazy code, you will. So that was talking about our FP16 and our int8 or S.8 instruction sets. But we didn't dedicate all the silicon just to new operations. You're actually seeing substantial performance improvements on our FP32 operations. So if you've coded stuff in FP32 for ResNet or in TensorFlow, and you're looking at ResNet or Inception, between our frequency improvements, our efficiency improvements, as well as adding more memory bandwidth, you can see up to 50% or even higher on some workloads as we continue to optimize them as well.
Just to clarify, it's the same version of ROCm running on the MI25 and the MI60?
Yes. I would not do anything. I would not do anything like that. And when you get the deck, all the claims and the documentation will be in the back end. So it scales very well across all data types, and also scales across multiple GPUs just using PCI Express Gen 4. So this compute acceleration is very scalable across multiple GPUs. It is a full enterprise class GPU for HPC, so double precision, ECC, and we've implemented RAS, reliability, accessibility, and serviceability, where you can actually capture errors, capture the poison, have the software determine what you want to do, if you want to halt, reset, and do it efficiently. It's secure, it's negotiated by our trusted root PSP system, so when you're talking about security, and especially with all the news the last little while, this has been very important for our customers. When we talk about HPC, compared to our previous V100, I don't want to talk about the numbers. I want to talk about the spread of performance. So if you look at these things, look at these things here. If you look at ResNet 50 and FP32 and TensorFlow, if you look at SGEM FP32 delivered performance, or DGEM FP64 delivered performance, you're really talking about a spread of about plus or minus 5% performance. So as we continue to optimize our software stack and develop it, and you've seen the year-over-year gains that you had in the ROCm stack, you can imagine that these things are continuing to push up, and the application level performance will be showing greater advantages across our silicon over time. So this is just a step, and hope to talk to you guys about this a little bit next year and show you how these charts compare against other competitive products. But across the board, we're competitive there, we're right there with Volta, and we're doing it with very versatile silicon as well.
Are these numbers using TensorFlow on Tesla V100?
This is using FP32.
Okay.
Do tensor cores accelerate FP32? No. But when you looked at, David did show some numbers before, where our FP16 performance, we're not as fast, but as you look at it, we have a scalable architecture in silicon that extends to int 4, int 8, int 8, FP16, FP32, and FP64 naturally. So we leave it to the discretion of the developer how they want to take advantage of the silicon. And you saw what we did with Chime, using S.8, and he's seeing substantial performance improvements there. So they can really tune it and optimize for their specific workloads.
So are these two cards in the same price range?
You're talking about V100 and Instinct MI60. So we're not talking about pricing right now because our initial offering of the Instinct MI accelerators will be either to data center customers, well, they'll be providing it to public cloud environments. So you'll be able to work it out at a sort of like per flop or however they want to per time slice, however they allocate it, or it'll be sold at a system solution level, either from a traditional OEM or an ODM. So it would be sort of incorrect for me to talk about a GPU price point when it'll be sold at a system level.
Why is that strategy?
That's generally just the way. Okay. That's our strategy of going to market with right now. We want to make sure that we're delivering a solid experience across our GPUs. We did talk about back at ISC, our ROCm validated solutions. We want to make sure that people can just grab our GPUs, get it from a validated partner, and it be turnkey. So David talked about this being the first PCI Gen 4 capable GPU. So this is where I want to sort of just highlight some details about scalability. So it is PCI Gen 4. it's twice the speed. I had a few people ask me, well, okay, tell me what this means, right? Well, this is a real benefit in two scenarios where you need to have fast GPU to CPU access for out-of-core workloads. So if you're going beyond the 32 gigabytes of data and you need to start paging out to the CPU and exchanging data, or if you're streaming data. So some early investigative numbers is showing, we're doubling the bandwidth. It could be anywhere between 1.5 to 1.6x benefit improvement from twice the bandwidth. As we get more PCI Gen 4 enabled systems out there, we'll share some more specific numbers. And as you can imagine, as our 7 nanometer CPUs details were shared, we'll start sharing additional information with that sort of synergy and ecosystem there. But we have 64 gigabytes of bandwidth from GPU to CPU. And then we have our Infinity Fabric link. So it allows us to connect up to 4 GPUs in a ring. It's 25 gigabaud of bandwidth, so 2 links, 100 gigabytes per second per link, so up to 200 gigabytes per second of GPU peer-to-peer bandwidth. The key thing here is that it is six times the speed of PCI Gen 3. Combine this, you'll have about exactly 264 gigabytes of bandwidth from GPU to GPU to CPU combined. And it allows you to have a unified memory access across all the GPUs. So, if you're paging out of 32 gigs, it allows you to have low latency access to well beyond 32 gigabyte. The GPU to GPU latency is about 60 to 70 milliseconds. Sorry, nanoseconds. And from a complete loop from one neighbor to another is about 100. Depends on the workload, anywhere between 140 to 170 nanoseconds. So very fast, low latency, large unified memory access, and it's all encrypted. The nice thing here is that you can actually use these connectivity in a virtualized environment as well. So David mentioned that we will implement hardware virtualization using SROV for compute. So what allows us to do is securely in a virtualized machine isolated environment connect up to from 1, 2, 4, and 8 GPUs in a VM. So if you have a 3 or 4U server, like we had it downstairs, the box system running Naples, you can fit 8 GPUs in there. You can have one VM take up all 8 GPUs. Each of the 4 GPUs connected to each other by Infinity Fabric link, and then between each of the hives or the nodes of the GPUs, you can communicate via PCI peer-to-peer. But you could split up the server in many different ways. You could have 2 VMs of 1 GPU, a VM of 2 GPUs connected versus Infinity Fabric link, and then 4 GPUs. You could have multiple clusters of 2 GPUs. So it's very flexible, but the key thing is it's isolated. You can do up to 8 GPUs, isolated from each other by hardware using SROV. And you can do it in a standard PCI CAM form factor as well. So you don't have to worry about high density interconnect backplanes or anything like that. So we're really making sure that this type of technology is widely accessible to everyone. So really what this is all powered on is we have a fast GPU, a highly scalable and flexible GPU, and it's all running on the backbone of an open source ecosystem with ROCm. So you talked to Derek and Ajit earlier today about our ecosystem. I won't detail on that, but we always like talking hardware. Everybody thinks AMD is a hardware company. I hope you appreciated the conversation with Ajit and Derek and the efforts that we're focusing on the software component as well, because that's what really allows us to extract every last little bit of performance out of it. So what you really end up here with these MI50 and MI60 accelerators is ultra fast, highly scalable, and completely open solution You have your 7 nanometer GPU, you have the fastest memory interface, you have the fastest double precision PCIe form factor, you have optimized deep learning operations all the way down to int4. You have full chip ECC, you have PCI Gen 4, you have Infinity Fabric Link, Infinity Fabric Link, enterprise class RAS, and it's all running an open source software ecosystem. So it's a very flexible solution, and we hope it's attractive to you, and we hope to hear some great feedback from you. Thank you. Happy to take some questions from you guys. Yes?
When you talked about the roadmap, you mentioned that MI60 will be used for virtualization or inference.
It can be. It can be. So,
but do you plan to announce new Radeon Pro or Tiny MI card for inference, for example?
so right now we're focusing specifically on MI50 and MI60 accelerators, but we do have customers saying we'd like to use your GPUs for large batch inference. We can support it with their int8 and int4 operations. We also support MX GPU SRLV technology, so you can actually have GPU time slicing as well. So it's a flexible architecture, and we will work with strategic customers to enable those use cases to have high reuse across the product stack.
Okay. So no more Radeon Pro for virtualization?
No, it's still there. So if you
On
look
new
here,
GPU?
let's go up here. So, so if you look here, we did announce our Radeon Pro V340 earlier this year. That product still coexists. You know, our primary focus for our Radeon Instinct products right now is machine learning training and HPC, but this was just an example of that the GPU is very flexible and it can be used in multiple different scenarios. So it really highlights the fact that we have a flexible GPU architecture and you're not locked into a one type of data type or something like that, or one specific use case that takes advantage of one particular data type. Okay. And Ian was giving me the hook out there, so I have to wrap it up. Thank you guys.
Thanks.
It's been a while. It's been a while.
No, it's,
Yeah.
Oh, it's a Munich conference. Yeah. There's no specific right now, but if you come here, you know, yeah. So at the end of the day, we didn't really tie the performance to the model numbers here. But if you look here, compared to MI25, you were at 24.7. We're actually more than twice as fast. So I really just want to say, hey, we're twice as fast. So it was just
inferencing,
yeah. So there's no real. It's not tied to an FP16 number or anything like that. It's really just we wanted to highlight that in particular workloads we're more than twice as fast. If you
Infinity Fabric.
if you look our performance here, in the FP16,
Vollgas ist ja noch.
we're there's about a 10% performance gap between MI50
Genau,
and
ja,
MI60.
die muss ja auch alles
So
dann passen,
even
ja,
an FP16
also,
performance will be twice as fast on MI25 with MI50.
Gut,
So we was really just highlighting the generational performance difference across products.
Aber während wir noch weiter Theorie ist gerade gelesen, dass
So it's a combination of multiple different factors.
ja. Aber das steht aber schon länger fest. Das haben sie quasi
Ja, aber
direkt gesagt.
aber so schnell.
Ja, nee, aber das hat uns
Die warten schon seit Ewigkeit.
Ich glaube, wir haben vor 2 Wochen schon gemacht, weil wir haben
1080 oder 1070.
mit Casing, ich weiß nicht, wir haben die Alarm abgekriegt. Vor 4 Wochen gesagt.
Yeah, so that's when you're not having to go out of core. Out of core.